Good morning, friends. So, today in this lecture, we will be seeing the numerical aspects of computation of selection differential and response to selection. So, as usual, first of all, we will see certain theoretical aspect, small portion of theoretical aspect, and then we will go for the examples. So, let us start with selection differential. So, what is selection differential? We have already studied in theory class that it is the difference of the individual who are selected for producing next generation from the original population from where they have been selected. That means, suppose you are having one population of 10 animals. So, out of these 10 animals, you chosen two animals, these two animals, one male and one female, and you chosen these two animals to produce next generation. So what we have to do, how this selection differential means, you have to take the performance of these two animals and you have to subtract the performance of average of these two animals with the average of the performance of population. That is called as selection differential. So what is if you see in the form of notation, selection differential is equal to PS bar minus P0 bar. PS bar means average of the selected population, these two, and P0 bar means original population, average of the original population, and S is the selection differential. Okay. Now this was about the selection differential. The next thing is, what is response to selection? So our aim in selection is to transmit whatever superiority. Actually, from selection differential, you have segregated the superiority of the population in form of selected individual. So now this superiority should be transmitted to next generation. What your aim is to transmit this superiority to next generation. But how much this superiority will be transmitted to next generation, that will be your response. Means, suppose in a farm you are going or you have been appointed as a veterinary officer in a farm, and now, or as a breeder in a farm, now your assignment is that the average milk production of farm is 5 liter per day, and the owner of the farm is willing that in next generation the average production should be 6 liter or 7 liter or 10 liter. It should be increased. So what you will do, you will go for searching animal in that population which are having milk production more than 5 liter, and at the end of the search you come up with two animals who are having milk production of around 8 liter and 9 liter. So what will be the average of selected individual? 8 plus 9 divided by 2, that means 8.5. So the population average was 5 liter and your selected individual's average is 8.5. So what is selection differential? 8.5 minus 5, that is 3.5. But this 3.5 is the selection differential. Now you want that this 3.5 liter should be transmitted to next generation. That means the progeny of these two individuals should produce more milk. How much more? More than 5 liter. So it will be always desirable that all the 3.5 liter, that is selection differential, get transmitted to next generation, but it is not like that. So in theory, if you see, the next generation should produce 5 plus 3.5, that is selection differential, that means 8.5 liter. But it is not like that. It will depend on the heritability. So the response of selection will depend on two things. The first thing is heritability of the trait, and another thing is the selection differential that we have already seen. So response to selection is equal to, so from here the formula comes, response to selection is equal to h square, that is derivative into selection differential. Now if you further expand this formula, you will get R, that is response to selection, is equal to h square into I. What is I? I is the intensity of selection, and sigma p. Sigma p is the phenotypic standard deviation. Phenotypic standard deviation of the trait. So why this is I into p? Because I is equal to S by sigma p. I is equal to S by sigma p. S means selection differential divided by phenotypic standard deviation of a trait. So in this way, you have expanded the formula of response to selection as heritability into intensity of selection into phenotypic standard deviation, because intensity of selection is equal to selection differential divided by phenotypic standard deviation. So regarding this intensity of selection, we will further see what is actually intensity of selection. In layman term, you may be knowing what is intensity, but here actually we will see what is intensity of selection. So you just concentrate on this graph. This is the normal distribution curve we have already seen when we were discussing about the different distributions in biostatistics class. Okay, so various type of distribution we had seen that there: binomial distribution, normal distribution, Poisson distribution. So this is the normal distribution. Most of the traits or most of the economic traits that we will encounter, or for the improvement of animal, the traits that we will consider, all the traits will be, most of the traits will be following the normal distribution. So this is the bell-shaped curve of normal distribution curve. Here, suppose on y-axis there is number of individual. So on y-axis number of individual, and on x-axis suppose it is milk yield. So on y-axis it is number of individual, on x-axis it is milk yield. So see, suppose milk yield is starting from 0 to 10 liter. 0 to 10 liter. So it will be 1 liter. Suppose this is 1 liter. Few individual will be producing 1 liter. Then 2 liter, the number of individual will be increased. 3 liter, further there will be increase. Suppose it is 5 liter. This point 5 liter. So maximum individual are producing 5 liter milk yield. Then 6 liter, again here 6 liter, again number of individual are going to reduce. Then 7 liter, 8 liter, 9 liter and 10 liter. So this is how the normal distribution, economic traits are normally distributed. Now what you decided, in your population of animals you are having average milk production of 5 liter, but you are having animals who are producing in the range of 1 liter to 10 liter. So now you decided that I will choose animal who is producing maximum, who is producing at least 7 liter. So just I will remove this. You have decided that I will choose animal who are producing at least 7 liter. So consider this point. So this point indicates 7 liter milk production. So you draw a perpendicular from this line and you go for all the animals which are lying beyond this point. So this, all the animals lying beyond this point is known as proportion of individuals. That means, and this point is called as point of truncation. This point is known as point of truncation. That means at that point you have truncated, you have made a point beyond which the animals which are lying beyond this level you will be selecting. So This is known as P, that is proportion of individuals selected, and the point where truncation was made is known as Z, that is either point of abscissa or point of truncation. Now I will read this. If the phenotype are distributed normally, selection truncates the distribution at particular point, that is height of ordinate. This is height of ordinate, and this is called as point of truncation. On x-axis, that is all individuals above that point are selected and those below are culled. So all the individuals below this point will be culled. The proportion of the selected animal is directly related to point of truncation. So suppose the point of truncation will be here. So the proportion, if this point of truncation is here, so this much will be the proportion of individual. So proportion of individual will be depending on the point of truncation. Now intensity of selection will be given by I is equal to Z by P. So what is this? Z is a point of truncation or point of abscissa, height of ordinate, and P is the proportion selected. So if proportion of individual will be increasing, intensity of selection will be decreasing. So now you have seen intensity of selection in two terms. First, in terms of phenotypic standard deviation, I is equal to S by sigma P, selection differential divided by phenotypic standard deviation, and another definition of intensity of selection, I is equal to Z by P. Z by P means height of ordinate divided by proportion of individuals selected. So now this definition was necessary because you have to understand how proportion will be regulating the intensity of selection. If proportion will increase, intensity of selection will be decreasing. If you will reduce the proportion, intensity of selection will be increasing. Now here I have made this I is equal to Z by P, and you have already seen I is equal to S by sigma P. So S is equal to I sigma P. So intensity of selection differential expressed in terms of standard deviation unit, that is phenotypic standard deviation, and that is why this intensity of selection is called as standardized selection differential, because S is equal to I into sigma P, or I is equal to S by sigma P. So S by sigma P means standardized, this is phenotypic standard deviation, and S is the selection differential. So intensity of selection is called as standardized selection differential. Okay. Now another related term is weighted selection differential. So the thing is that the concept of selection differential was okay, we have already seen. Now the problem is that that concept of selection differential will only work when each and every individual is producing equal number of progeny. Each and every individual that you have selected is producing equal number of progeny, but it will not be in reality, because every individual will produce different number of progeny. So in that case, if you are going with that selection differential, it will be wrong. So for that, you have to go with weighted selection differential. Actually, when I was discussing the measure of central tendency in unit 1, there I had already told you about the weighted mean. So the weighted selection differential draw its concept from weighted mean. So what is weighted selection differential? So the earlier selection differential that we have discussed, I am telling that selection differential as observed selection differential. So observed selection differential obtained on assumption that all the selected parents are contributing equal number of progeny to the next generation. But the fact is that each parent should be weighted by number of progenies it contributed to the next generation. It is not always that each parent will contribute equal number of progeny. So in that case, what you have to do, you have to calculate the weighted selection differential, and weighted selection differential is nothing but it's an average based on their weight in terms of number of progeny. So summation xi divided by n. So what is xi? Xi is the observation on ith parent, and ni is the number of progeny produced by ith parent, and it should be subtracted by the population mean. So this is herd or flock mean or population mean. So this is how you are calculating the weighted selection differential. Now with this much theoretical concept, we will proceed towards the numerical example. So first of all, we will find the selection differential, numericals based on selection differential. So it is not possible to cover all the numerical questions in this video. So what I have done, I have taken some representative numerical questions, and based on that you have to draw the idea from these numerical questions, and then you have to calculate other numerical questions that you will be getting on your practical manual. So, and if you are finding any difficulty, you just let me know. Now the first example is from the data given below. Estimate the genetic gain per year. So this is about the response to selection, that you have to draw the genetic gain. So one thing I missed in theory portion, R is equal to response to selection. This is also called as genetic gain. Genetic gain. So response to selection and genetic gain is one and same. So what here have to calculate? We have to calculate the genetic gain per year. You have to mind it, per year. Now heritability of the trait is given 0.35. Selection differential is 250 kg and generation interval is 6 years. Generation interval is also very important. Now you know the formula for response to selection. R is equal to H square S. H square S. You know H square is given 0.35 and S is selection differential, it is 250. So R should be 0.35 into 250. So how much it will come? But the thing is that this R 0.35 into 250 will be response to selection in one generation. One generation means 6 years. Generation interval is 6 years. But the question is telling you have to find the genetic gain per year. So what you have to do? You have to divide this term, that is 0.35 into 250 divided by 6. 6, that is generation interval. So in this way you will get the response to selection per year or genetic gain per year as 14.583 kg. 14.583 kg. So what will be your interpretation? Your interpretation will be that population mean will be changed by 14.58 kg per year. So in 6 years, the total change you will be able to make in 6 years. But if somebody is asking what will be the genetic gain per year, then you have to divide the response to selection by generation interval, and then you have to interpret that this much genetic gain per year will be obtained in the selection that we are performing. Now the next example is about the weighted selection differential. So in a broiler flock there are 5 cocks, and there is a broiler flock, and out of those broiler flock you have to select 5 cocks, and the basis of selection was 6 week body weight, and now this 5 cock will act as sire in the next generation, sire to produce next generation. If the flock mean of 6 week body weight was 12 to 6 gram, that means your P0 bar is given 1226 gram. So now the other observations are given here. So this is sire number or cock number 1, 2, 3, 4, 5, body weight of all the 5 cocks and the number of progeny those cocks are producing in the next generation. So here you can see the variable number of progeny produced by each sire. So total progeny is 78. Now you have to find out the weighted selection differential. So how you will find the weighted selection differential? Just see, the population mean is given 1226 gram. Then what is the mean of selected parent? So mean of selected parent we have already seen. You just see the previous slide. The total body weight was 7680. 7680 is the summation divided by total number of parents will be there. So here you can see 7680 divided by 5, that is 1536 gram. So your P0 bar was 1226. PS bar is 1536. 1536 you have already calculated. Now what will be the observed selection differential? So observed selection differential will be 1536 minus 1226, that is 310 gram. 310 gram. But this will be followed only when each and every parent is producing equal number of progeny. But it is not like that here in this question. So what you have to calculate? You have to calculate the weighted selection differential. So weighted selection differential will be summation xi ni divided by n minus population mean. So here now you can see the previous table. I will again show you. Just see, 1720 into total number of progeny is 10. Then 1640 into total number of progeny 15. Like that you have to calculate. Just see how I have calculated here. So 1740 into 10, 1640 into 15, and likewise 1530 into 16 divided by total number of progeny, it was 78 minus population mean. Population mean was 1226 gram. So in this way, if you calculate, you will get the selection differential as 280.41, whereas observed selection differential was 310 gram. So you can see the difference of almost 20 gram, more than 20 gram. So this much, this observation will be biased, or there will be error associated with the observed selection differential. So in this case, where the number of progenies are variable, there you have to go with weighted selection differential. I hope the difference between observed selection differential and weighted selection differential is clear to you. So in this lecture, I have covered response to selection, selection differential, and weighted selection differential, genetic gain. I have tried to give you the synopsis of theory and then one or two numerically solved example. So based on this numerically solved example, you go and see the various numerical questions that has been provided in your practical manual. You try to solve it, because in each numerical question will be unique in their own way. But you have to find out, there will be few things, few tricks will be there, few indirect questions will be there, but the concept will remain same. So I think you will be able to solve all the numerical questions given in your practical manual. And if you are finding any difficulty, just let me know. Until then, thank you. Bye bye.